So how do we get humans to Mars safely? This is an unsolved challenge due to three core barriers. First, transit time. Chemical propulsion takes 6 to 9 months one way, which can dangerously prolong radiation exposure. Second, radiation itself. Cosmic round-trip ray doses may exceed safety limits for our astronauts, as well as hardware and software. Third, fuel mass. More shielding adds more weight to the ship, and that requires more fuel to maintain a consistent amount of speed. Each fix and optimization we make to one will worsen the other factors, which means we have to choose the most appropriate propulsion system.
This slide compares 3 different propulsion systems: NERVA, nuclear thermal propulsion, nuclear electric propulsion, NEP, and chemical propulsion. We compared these systems based on how they work, how much thrust they produce, how quickly they accelerate, and how much radiation exposure astronauts would experience. Starting with NERVA, which stands for Nuclear Engine for Rocket Vehicle Application. The process begins with liquid hydrogen being pumped into a nuclear reactor. Inside the reactor, uranium fuel undergoes controlled fission reactions that generate a large amount of heat. That heat is then transferred directly to the hydrogen, turning it into an extremely hot, high-pressure gas. The gas then exits through a nozzle, creating thrust. NERVA produces a high amount of thrust while also being much more fuel efficient than chemical rockets. This combination allows the spacecraft to accelerate quickly while using less propellant. One major advantage is radiation exposure. There are things called Van Allen belts, which are 2 massive rings of high-energy radiation trapped by Earth's magnetic field. The zone acts as a protective shield for Earth, but creates a hazardous area of trapped protons and electrons, leading to high radiation. Because NERVA can accelerate the spacecraft faster, astronauts spend less time passing through Earth's Van Allen radiation belts, which lowers their overall radiation dose. Next is nuclear electric propulsion, or NEP. Instead of directly producing thrust from heat, the reactor generates electricity. That electricity powers ion engines, which convert gases like xenon and argon into plasma. Magnetic and electric fields then accelerate the plasma and inject it out of the engine. NEP is incredibly efficient, but it produces very little thrust. Instead of accelerating quickly, the spacecraft gradually builds speeds over several months. Because of the slow acceleration, astronauts would remain in the Van Allen belts for a much longer period of time. Finally, we have chemical propulsion, which is a system used by most rockets today. Chemical rockets work by mixing fuel and an oxidizer through a combustion chamber. The chemical reaction produces extremely hot gases that are expelled through a nozzle to generate thrust. Chemical rockets produce enormous amounts of heat, which is why they're ideal for launching off of Earth. However, they require a huge amount of fuel and are much less efficient for long-distance missions to Mars, especially since our rocket will be launching from space. After comparing all 3 systems, we determined that nuclear thermal propulsion was the best option due to speed and the safety of our crew in regards to the risk of radiation.
Nuclear thermal propulsion. Nuclear thermal rocket engines utilize the heat generated by a nuclear reactor to superheat cool liquid hydrogen that has been chilled, resulting in a very fuel-effective propulsion. Nuclear thermal programs have existed since the 1960s and were at one time considered the premier way to send people to Mars. Reactors from this propulsion system can be used without producing thrust from the engine in certain configurations. Now, here are our engine specs. We have a combined thrust of 150,000 pounds force with 2 75,000 pounds force engines. Our ISP, or the measure of how long an engine can produce a pound of thrust for 1 pound of propellant, is 887 seconds, and it's 1437 seconds with the wave rotor attached. Now, the max heat in Celsius that our engine can withstand is 2,427 to 2,727 Celsius. Anything higher than this, and the reactor components would melt, causing a literal meltdown within the reactor. Now, the flow rate is 84.5 pounds per second. Our chamber pressure is 450 psi, and our radiation produces 2 to 5 rem. Our nuclear reactor, here you can see 2 diagrams of our nuclear reactor. You can see the control drums, the reflectors, and the actual reactor itself, and you can see how we're going to be pumping hydrogen through the reactor, causing it to expand and produce thrust. Now, the wave rotor is a rotating turbo machine that utilizes internal channels to generate shock waves that compress and heat hydrogen. The way this works is that We pump supercooled, very high pressure hydrogen into a separate channel from where the byproduct of our highly expanded hydrogen is. Now, these two things will flow into a channel where the very heavy hydrogen, or the very light hydrogen, let's say, the expanded hydrogen will flow into a channel where it is very hot, and this channel will then spin. Now, the other hydrogen, the very super chilled and high pressure hydrogen, will be exposed to these channels very quickly, resulting in shock waves being generated. These shock waves will then allow heat up and compress the hydrogen, resulting in temperatures between 2,876 Celsius and 4,926 Celsius. Now, the actual materials of the chamber itself will only be exposed to the cooling and a hot hydrogen for a very short time, allowing it to average itself out, and the material does not withstand that much heat or pressure. And by utilizing this technology, we can increase our exhaust velocity to 1,437 seconds. Escape our specific impulse. Now, here is our wave rotor diagram. As you can see, the rotors are where our superheated hydrogen will be exposed to the cool hydrogen and expanded. And the inlet ports represent where we will be pumping in the cooled hydrogen and the very hot hydrogen. This is not an exact replica of what we intend to use, but a similar model. Now, overview of our trajectory. For the Earth-Mars transfer orbit, we will be using a Type 1 orbit, meaning we'll go less than 180 degrees around the Sun. And for the Mars-Earth transfer, we'll have to use a Type 2 orbit, which means we'll go more than 180 degrees around the Sun. So we will be launching from the ISS orbit in LEO, or 408 kilometers above the sea level. We will depart Earth April 27, 2033, spend 84 days in transit to Mars, stay 14 days in Mars's orbit, then fly back 200 days back to Earth, returning February 19th, 2034, for a total of 298 days flight time. Our nuclear thermal engines and wave rotor allow us to utilize very high delta V orbits, cutting mission duration significantly compared to conventional engines. Comparisons of the delta V in fuel and time required for our different engines. As you can see, if we were to use the most optimal orbit for a chemical engine, we would have to bring 1,090 tons. We would have to use, the orbit would require a delta V of 7.6618 kilometers a second. Our time would be 398 days, so we'd have to spend a very long time in space comparatively, and our delta V left over would be 1.274, which would not be enough to deposit us in a parking orbit around around Earth. Now, the NEP requires the least fuel out of all of these engines, and it also allows the highest delta V orbit, but it would take us 900 days to get there, which would be an unacceptable amount of time spent in space, and we would have very little delta V left over. Our NTP engine, which without our wave rotor, would make us bring 298 tons, so a little over a third of a chemical rocket. We would have to use a delta V of 7.9353 kilometers per second, and we would have a time of 354 days spent in space. So pretty quick, but still an unacceptable amount of time spent in space. And we would have 0.0351 kilometers per second of delta V left. Now, our NTP plus wave rotor, which is the current configuration we have set up, only makes us bring only 192.7 tons of fuel. It allows us to use a high delta V orbit of 9.462 kilometers a second, and our time would be 298 days. We would have 3.3874 kilometers of delta V left over, which would allow us to establish a parking orbit in mid-Earth orbit, allowing us to reuse the spacecraft for future missions. Is a picture of our orbit. The green leg represents our outbound transit to Mars. You'll be spending 2 weeks at Mars and then coming back to Earth utilizing the pink orbit. As you can see, it's a little way longer than the other orbit, and we will be intersecting the Earth at a later point. Yeah. There are many ways to generate power in space. These include solar panels, radiothermal generators, which are used in deep space probes such as this is a Voyager spacecraft, nuclear reactors, and long-term batteries. Now, we can't use solar panels as they wouldn't be effective enough out in deep space. Radiothermal generators don't provide enough of our power, and long-term batteries are out of the option. So our only option left is our nuclear reactor. Luckily, we have two of them on board. Now, when we switch our engine to its stationary slash non-thrust producing mode, it behaves kind of like a power plant. So it operates as a closed loop Brayton cycle where the hydrogen working fluid is reused, allowing for a turbine and alternator to generate 9.8 to 14.7 megawatts electric for the switch systems. Now, according to the paper we based this system off, the turbine and alternator have 95% efficiency. Now, I don't know if that efficiency is perfectly accurate, which is why our megawatts electric is so high, but it's assumed that this has 95% efficiency for the turbine and alternator. Now, the reactor, because of this, also maintains a much more cooler core temperature, approximately 2000 Kelvin, which preserves the fuel by reducing the thermal stress and fission product buildup during our power generation. So it doesn't get as hot as it does when it's shooting out the liquid hydrogen, which is very good for preserving our components. Now, here is a picture of the Brayton cycle. As you can see there, here's our heat exchanger, which is the reactor itself, which is producing the heat, the turbine, which spins and produces the work, producing our electricity, our heat exchangers, which are radiators on board the spacecraft, and our compressors, which compresses the liquid hydrogen and compresses the hydrogen to a liquid form and runs it through the actual reactor itself. Now, as you can see here, this is a visual of how much power we've been producing. So the average US home produces 1.2 kilowatts. The ISS produces 100 times that at 120 kilowatts, and we're producing about 8,333 homes worth of that, or close to about 10,000 times more power, which is insane, 10 megawatts, and that's the low end of our spectrum. Now, our shielding for our reactors utilizes an internal shield made of borated aluminum titanium hydrate and lead, alongside an external shield comprised of lithium hydrate and tungsten. Now, these shields can be configured as a directional shield, meaning that the radiation is diverted out to the sides and back of the spacecraft and protected from the front, or a two-ply configuration where it is protects the entirety of itself, allowing the crew and environment around it to move around and inspect the reactor from all sides. By strategically placing the crew module in the reactor's shadow, the shielding limits their engine radiation dose from 2 to 5 rem, which is the yearly allowed dose for nuclear reactors on Earth. As you can see here, this is a picture of our reactor shielding and how it works. That shadow shield is our shield, and as you can see here, the radiation is shot out in all its directions except directly in front of the spacecraft, where it's protected by the crew compartment. If we sent crew out while the reactor was in this directional shielding configuration, they would probably receive a much higher radiation dose than they would in the 2-pi configuration.
This slide shows the overall design of our spacecraft that will be used for our mission to Mars, created by our CAD design team. Starting on the left side, we have our command module, which acts as the flight deck and the astronauts' living quarters. It would contain navigation systems, communication equipment, computers, sleeping areas, exercise equipment, and would be the primary area for our astronauts. Above that is an additional storage compartment. Since this is a long-duration mission, astronauts need enough supplies to survive for several months. This area would store food, medical supplies, and other necessities. Next is the cryo storage / life support and docking port. The docking port allows other spacecrafts or supply vehicles to attach to the spacecraft if needed, and us to attach to the ISS if needed. The cryogenic storage system is especially important because it contains our life support systems that provide oxygen and regulate temperature. In the center, we have the radiators. Nuclear systems in space lead to excess heat. Since space is a vacuum, we can't get rid of the heat in the same way we do on Earth, and instead must use radiators to release excess heat into space to keep all systems safe from overheating. In between the cryogenic tank and the radiators is a storm shelter. In the Van Allen belts, astronauts are exposed to extremely high levels of radiation. This area would provide extra protection during solar storms and periods of increased radiation exposure like in Van Allen belts. The section after the radiators is the liquid hydrogen, or LH2, propellant tank. Liquid hydrogen was chosen because it is extremely efficient when used with nuclear thermal propulsion. It will be stored at around negative 253 degrees Celsius in its tank. We also have the truss structure in the middle, which connects the whole vehicle together and distributes forces throughout the design. At the back of the spacecraft, there are 2 nuclear reactor cores. These reactors use controlled nuclear fission to generate enormous amounts of heat to power all systems of the spacecraft. Finally, we have the thrusters. Liquid hydrogen is pumped through the reactor, where it is heated to extremely high temperatures. It then rapidly expands and is expelled through the nozzle, creating thrust that propels the spacecraft forward. Overall, this design focuses on reducing travel time to Mars, keeping the astronauts safe, and providing them with the resources they need for this long journey.
As we leave Earth's gravitational field, the decrease of the natural gravitational force has a severe impact on the human body, and as head of the Biology and Health Department, we're aiming to mitigate those risks. Our crew risks the deterioration of bone density, muscle, and the loss of blood flow in the lower body, risking serious injury and possible death. Our first idea to solve this was to create a centrifuge, which is a spinning donut-shaped spacecraft that would artificially create gravity using centrifugal force pushing objects outwards. However, this idea was expensive and cost inefficient. Instead, our solution is to have the crew exercise on the trip with the use of the flywheel, a device similar to the rowing machine and seen on the image in the bottom right. For basic human necessities, we use numbers that were calculated from the ISS and past space mission trips for 300 days and 5 astronauts. Our crew size, as noted earlier, is 4 astronauts. This overestimate ensures any space delay does not compromise health. We have 938 kilograms of hygienic and drinking water, 138 kilograms of food including packaging, and 563 kilograms of air on board. We also have 21 kilograms of medical supplies and the HSP on board. The HSP is a health stabilization program that we put our astronauts on before the trip, where we quarantine the crew to prevent infection of disease during the mission. The average quarantine duration is 14 days, but because our trip is longer, we will do 21 days. We have 57 kilograms of hygienic supplies and 173 kilograms of clothing. Our weight for clothing was much higher before, but after researching and implementing new advanced antimicrobial fabrics, particularly from the company X-Static, we dramatically reduced the weight from clothing. We also used NASA's Environmental Control and Life Support Systems, known as ECLSS. The system weighs 4,000 kilograms and uses 31 kilowatts per day to operate. Aspects of the system are a water recovery system that recovers 98% of water, and the oxygen generation system that uses cabin humidity and urine to break H2O into hydrogen and oxygen gas, and a CO2 removal system that keeps the crew from CO2 poisoning. This system bumps our total gear weight to 6,442.3 kilograms. Other sources of energy include our fridge and electric resistance heater is 18 kilowatts per day. While most spacecraft rely on emitted heat from computers and other electronics in the spacecraft, the cold environment near Mars, which is usually negative 60 degrees Celsius, requires the electric resistance heater. Lights produced 0.25 kilowatts per day, making our total 50 kilowatts per day with everything listed. There's a high threat of radiation on our mission, since we are traveling in interplanetary space. Our biggest threat of radiation are galactic cosmic rays, or GCRs, that have an effect of 149 to 298 rem unshielded. NASA's astronauts have a career radiation limit of 60 rem, making the risk from GCRs 2.5 to 5 times the amount they can be exposed to. 450 rem has a 50% chance of fatality. Also, another threat is the Van Allen belt, which emits 0.5 rem to 2 rem per hour based on shielding. The issue rises with costs. Surrounding the spacecraft with heavy shielding is expensive, but not as expensive as researching more effective materials. So we created a plan for shielding, increasing the weight of the spacecraft. Our plan is to use hydrogen fuel tanks between the reactor and living quarters to shield from the radiation of the engines, which decreases the amount of REM by 20 to 30%. Next, we will use graded Z passive shielding throughout the ship, decreasing another 10 to 15%, and include heavily shielded storm centers on the ship made with high-density polyethylene, decreasing another 25% in REM. In addition, we will have our crew wear AstroRad vests to protect vital organs, such as the GI tract, from human radiation. The weight for reducing the harm of radiation is 5,800 kilograms total, which will also add to the cost of fuel we will need to launch. Our shielding cuts 35% of all galactic cosmic ray radiation, and storm shelters reduce 25% of radiation during solar particle events. In total, we have 100 to 215 rem of GCR radiation, and we spend about 3 hours in the Van Allen belts, coming to a total of 1.18 rem of radiation exposed when in the belts. The REM exposure from the Van Allen belts is not a threat, as getting a CT scan is roughly 1 rem.
Moving on to the finance department. This is broken down into 3 main sections, the first being the reactor and fuel. This comes out to about $27 billion, with the majority of the cost being dedicated to the reactor and propulsion system, as well as the transit vehicle. Another notable cost would be the research and development and mission infrastructure, which are currently set to about $5 billion, but are subject to change throughout the course of the project. Next is the software development, at a total of $590 million. The most notable costs are GNC software at $200 million, the nuclear reactor control system at $100 million, and the communication and simulation software at $100 million combined. Finally, we have the crew and life support at $3.04 billion. The environmental control and life support system covers the bulk of the budget at $2 billion. Crew training would be $1 billion, and the other factors like crew necessities and life jackets would be $44 million combined. To protect from radiation, an HDPE shield would be used at $105,000. In total, the entire mission would cost about $30.63 billion. And just to note, this is a rough estimate subject to change, and all finances were estimated from NASA's database. This project spans 7 years, starting with the research and planning phase, also one of the least costly phases, which makes up 15% of the budget. Phase 2, where all the construction and building occurs, is the most costly phase at 55% of the overall budget, and the next phase, Phase 3, which is testing and crew training, is 20% of the budget. And finally, launching operations makes up 10% of the budget.
This is Demairo, and this is for slides 29 and 30. Most people think that the hardest part of getting to Mars is the engineering. Once you place a nuclear reactor in a spacecraft, though, multiple federal agencies and international laws become involved. In reality, none of this launches without legal approval. One of the first approvals our mission would need is a presidential authorization under NSPN 20. This is a newly created policy in 2019, and this establishes a legal framework for nuclear space missions. Because our spacecraft uses nuclear technology, we would need to meet these requirements before any launch. We would also need an FAA license and a re-entry license. This is much more than a simple permit, it's rather a collection, and this review process can take years and examines rocket safety, crew safety, flight procedures, and financial responsibility. We would need an environmental impact statement reviewed by agencies such as NASA and the EPA. This document evaluates the environmental risks of the mission, and especially what could happen if a launch failure, God forbid, occurred while carrying a nuclear payload. Another major requirement is the payload review process. The U.S. government is internationally responsible for the actions of spacecraft that it authorizes, so every payload must be reviewed for compliance with national security, foreign policy, and international law. This includes the 1967 Outer Space Treaty, which still helps govern space exploration today. We would also need approvals from the Department of Energy, the Department of Transportation, and the Department of Commerce. Because a commercial nuclear-powered mission to Mars is something that's never been done before, there are still legal gray areas that current regulations do not fully address. As one of the first missions of its kind, our project will not only follow existing laws, but help shape future regulations for deep space exploration.
As far as software goes, we can divide this into 4 main departments. First, guidance, navigation, and control. We want to maintain 6 degrees of freedom for the ship, utilizing quaternion math, common filters, and reaction wheel loops. As well, we want low thrust optimization algorithms to steer the continuous nuclear electric burns appropriately. As well, we want autonomous navigation. We'll make use of NASA's Auto-NGC using their CFS architecture, as well as power descent entry, descent landing, guidance for Mars landing. Second, we want reactor and flight software. We have to make sure the reactor stays under control, the drums, the rods, as well as the neutron flux and thermal balancing. We're going to implement radiation-hardened CPUs with software voting to catch cosmic ray bit flips, and like I said before, we're going to use NASA's CFS due to it being extremely modular. Third, we want to make sure we have autonomy, comms, and ground control. Any kind of fault management can be handled with machine learning and FDIR systems. The light delay would make human reaction too slow if we want to control this from the ground. As well, we can use NASA's Deep Space Network Communications System and AS-256 to block any kind of command spoofing, so anything unwanted will not go through to our ship. Then we're going to have the dashboard and digital twin simulation be implemented so we can see how the ship would react to any kind of commands that we would send upstream. Lastly, we want to make use of embedded systems and the hardware interface. So what we are going to be doing is central drivers and actuator controlling software to the physical spacecraft, and then also use power management system to balance reactor output across subsystems, and finally real-time loops running microseconds on the radiation hardware so we have the fastest speeds possible. Now what's next? In the next year, we're going to finalize the engine and thrust design basis, completing the full CAD model and tightening the cost and shielding estimates. After that, begin the engine and reactor ground testing, which is going to take the longest amount of time. Then, in the midst of that, we're going to secure any kind of permits, authorization, and contracts with any other companies we may be involved with, such as SpaceX. And then in 2029, we're going to start actually building the physical spacecraft, training and selecting our crew. 2030, we're going to do a unmanned test flight and just everything else we need before the true launch window. Overall, the problem is that we have to minimize transit time, radiation dose, and fuel mass all at once. But if we improve any one of those, it's going to usually worsen the other one.